Welcome back to this course on multi-core systems. In this lesson I will present an example read, modify, write instruction called test and set. I will also present two methods to improve the efficiency of a spin lock implemented using test and set. A read, modify, write instruction is an instruction that reads a memory location and sets it to another value. Furthermore, the read and the write are executed atomically. It cannot be divided. In addition, it returns a value from which it can be deduced if the read, modify, write instruction was successful or not. As a side note, the word atomic is derived from atom, as shown here. Because for a long time mankind believed that atoms could not be divided. Modern physics, however, has shown that atoms can be divided. Probably the simplest atomic read, modify, write instruction is called test and set. This instruction reads a memory location and sets it to the value 1. Here's an example. T and S R1 lock. This instruction reads memory location lock into R1 and atomically, which I indicate by this circled plus operator here, sets the memory location lock. If after executing this instruction R1 equals 0, then the test and set was successful. If it is not, if it is unequal to 0, it was unsuccessful since the lock was already set. As another side note, there is no test in test and set. So it should have been called actually load and set or read and set. But I will stick to the classical name test and set. Let's now look at how the lock operations acquire and release can be implemented using test and set, but this time correctly. Here's the acquire operation. First, we test and set the lock. We load the lock variable into a register R2 and set the lock variable to 1. Then we test if the lock was already set and branch back if it was. In other words, if R2 is unequal to 0, we branch back to the test and set. If the lock was free, then control flows to this instruction. We, meaning us, the calling thread, was successful in acquiring the lock and we can enter the critical section. The implementation of the release function that frees the lock does not have to be modified. We simply clear the lock variable and return. There is no issue here. Let's now sketch how the test and set instruction might be implemented. If locks cannot be cached, the memory controller can enforce atomic execution by first executing the load, then a store of 1, and finally by returning the load value as sketched in this figure. Of course, the memory controller may handle no other memory requests in between. The biggest problem of this solution is that locks cannot be cached, which implies that the acquire operation incurs a long latency and that a lot of traffic will be generated. The second solution allows locks to be cached. In this case, we should treat test and set as a store, which implies that all other copies of the block containing the lock variable need to be invalidated before the store occurs. Let's now study the efficiency of acquiring a lock when locks can be cached. The problem is that a spin lock that repeatedly reads and writes a memory location until its value becomes 0 may generate a huge amount of coherence traffic. To see why, consider this scenario. 3 threads try to simultaneously acquire a lock. The lock is held by thread T0, so threads T1 repeatedly read and write it. Initially, the lock is in state modified in thread T0, the node executing T0, and in state invalid in the nodes executing T1 and T2 respectively. T1 does a test does a test and set on the lock. For that, it needs to invalidate the copy of T0. T0 invalidates its copy and sends back an acknowledgement to T1, which now has the lock in state modified. But then T1 finds the lock is already set, so it stays in its busy waiting loop. Then thread T2 wants to acquire the lock. For that, it needs to invalidate the copy of T1. T1 invalidates its copy and acknowledges this back to thread 2, which now holds the block in state modified. But the lock is still being held by thread T0, so T2 also stays in its busy waiting loop. And now T1 again performs a test and set. It needs to get and invalidate the copy from T2. T2 invalidates its copy and acknowledges this to T1, which now holds again the lock in state modified. But still the lock is kept locked by T0. So T2 wants to acquire the lock. For that, it needs to invalidate the copy of T1. T1 invalidates its copy, acknowledges this to T2, and so on and so forth. I don't know if you notice it, but we were playing a game of ping pong here. We're ping-ponging the lock between the caches of T1 and T2. And we're not very good at playing this game since we generate a lot of coherence traffic. What can be done about it? A test and set, even if the lock is cached, is costly since it involves a write, and for every write, all other copies need to be invalidated. Somehow we need to reduce the frequency, the number of times the test and set instruction is executed. I discussed two approaches for doing so. The first approach is called test and set with exponential backoff. It works as follows. Every time we read the log using test and set and determine that the log was set, we pause for a while. The pause can be a constant number of times, but with exponential backoff, the pause is increased by a constant factor c. The idea behind exponential backoff is that it doesn't make sense to keep trying to get the log if it is held for a long time. The second approach is called test and set. It works as follows. First, we load the log using a normal load. Then we test the log value. If it was already locked, we repeat. If it was unlocked, meaning its value was 0, we try to get the log using test and set. Here's how it can be implemented. First, we load the log using a normal load into a register. Then we test if the log is locked or held. If it is, we repeat it. If it is free, we read and write the log using test and set. This test and set is necessary because there may have been another nasty thread between the load and this test and set that has acquired the log. If the test and set failed, meaning the log was already set, we repeat. Otherwise, we can return to our caller because the test and set was successful. And we, more precisely, the calling thread successfully acquired the log. The benefit of this approach is that it works well with caches. The processor can spin on its own local copy of the log variable as long as the log is held. Since read hits don't generate bus traffic, this considerably reduces bus traffic. Only when the thread holding the log releases it, it will invalidate all other copies, forcing the threads trying to acquire the log to fetch it again. This concludes this lesson. Thank you for watching. In the next lesson, I will describe some other atomic read, modify, write instructions beside test and set. Hope to see you back.